Standard OLS assumes a simple location shift, where the effect is constant across the entire distribution. However, as we see in the location scale shift graph, reality is often more complex. Economic policies frequently affect different groups in unique ways. For instance, 401k eligibility might significantly increase wealth for high savers while having little to no effect on low savers. OLS masks this heterogeneity by only estimating the effect on the mean outcome. Furthermore, when endogeneity is present, such as individuals self-selecting into 401k plans, standard quantile regression falls short. This is where instrumental variables quantile regression, or IVQR, provides the necessary solution by combining distributional detail with causal identification. This flowchart provides a clear roadmap for selecting the appropriate instrumental variables quantile regression command based on your data structure. Your decision starts with whether you have panel or cross-sectional data. For panel data, the method of moments approach using commands like mmqreg or xtqreg is standard. For cross-sectional data, the choice within the official IVQregress suite depends on model complexity. If you have a single endogenous variable and require rigorous inference with weak instrument tests, IVQregress IQR is the best fit. Conversely, for multiple endogenous variables or models where speed is a priority, IVQregress Smooth is preferred. As a key Stata tip, remember that the official suite introduced in Stata 18 supersedes older community commands like IVQReg and SIVQR, though mmqreg remains the standard for panel data with fixed effects. This table provides a comparison of the most common Stata commands for instrumental variables quantile regression. The official IVQregress command in Stata v18+ is the current standard, offering robust diagnostics and weak IV support, though it's computationally heavy. For speed, the community-contributed SQIVR is a strong alternative. mmqreg is specialized for panel data with fixed effects, while the legacy IVQreg is now largely superseded. As David M. Kaplan famously said, "None is better or worse, just appropriate for different applications." Now, let's look at the intuition behind the IQR estimator to understand why these choices matter. The core intuition of inverse quantile regression, or IQR, is based on an iterative search process. Because of endogeneity, we cannot directly minimize the distance between y and x as we do in standard quantile regression. Instead, we follow a logical cycle. First, we select a potential value, or a guess, for our structural parameter alpha. Second, we clean the outcome by subtracting this guessed effect from y. Third, we test our instrument by regressing this cleaned outcome on z. Finally, we ask, is the coefficient of z 0? If not, we refine our guess and repeat the process. If it is 0, we have found our solution. Mathematically, we are searching for an alpha tau such that the quantile of the residual, y minus d times alpha, is statistically independent of the instrument z. We want to find the parameter that makes the instrument irrelevant to the residual. To ensure our causal identification is valid, we must satisfy 5 pillars. First, potential outcomes. Outcomes must be related to covariates via a structural quantile function. Second, independence. The instrument z must be independent of the unobserved error u. Third, selection. The endogenous variable d must be statistically dependent on the instrument z. Fourth, rank similarity is highlighted because it is key for interpretation. It assumes an individual's unobserved rank, like innate ability, stays the same across treatment states. A high saver without a 401k remains a high saver with one. Without this, we can only see general distributional shifts, not individual causal effects. Finally, monotonicity. The structural function must be strictly increasing in the rank variable. Together, these 5 assumptions anchor our analysis. The coefficient alpha tau represents the change in the specific quantile of the outcome for a unit change in the endogenous variable. This reveals heterogeneity, showing how a policy might benefit the rich significantly more than the poor. For instance, while OLS might show an average wealth increase of $5,000, IVQR could reveal it only increases wealth by $1,000 for the poor, but by $10,000 for the rich. Ultimately, IVQR reveals heterogeneity, demonstrating how policies affect the top and bottom of society differently. Now, let's dive into the practical implementation with the official Stata syntax for the ivqregress command. The command structure follows a logical flow. First, you specify the estimator. You'll typically choose IQR for maximum precision when you have a single endogenous variable, or smooth if you need speed or have multiple endogenous variables. Next comes the outcome variable, denoted as depvar, followed by any exogenous controls in the first variable list. The core of the IV specification is held within the parentheses. Here, you list your endogenous treatment variable set equal to your instrument. Finally, after the comma, you add options for quantile selection and variance estimation. Looking at our example at the bottom, we are using the IQR estimator to see how 401k eligibility, acting as our instrument, influences participation to affect financial assets across the 25th, 50th, and 75th quantiles. When implementing IVQR in Stata, fine-tuning your setup options is critical for both precision and reliability. Use the quantile option to specify which parts of the distribution you want to analyze. The default is the median, but for a full picture, you might estimate every 10th percentile. For variance estimation, the VCE option allows you to choose between robust standard errors or bootstrap inference, which is required for certain post-estimation tests. If you use bootstrapping, the reps option is crucial. I recommend at least 100 replications for preliminary checks, but you should use 1,000 for any final results intended for publication. For advanced users of the IQR estimator, you can adjust the search grid density with ngrid or manually set a search range with bound if the coefficients fall outside the default areas. Finally, always remember the Stata tip. Run estat walled plot after your estimation to visually confirm that the search algorithm successfully found a global minimum, ensuring your results are mathematically sound. Welcome to the first practice step, data preparation. In this exercise, we are estimating the effect of 401k participation on net financial assets. Our model includes assets as the outcome, P401k as the endogenous treatment variable, and E401k as the instrument. Skewed, meaning OLS mean regression might provide a misleading picture. This motivates our move towards quantile methods. Now that we've prepared our data, let's execute the model. We use the ivqregress IQR command to estimate the effect of 401k participation on financial assets at the 25th, 50th, and 75th percentiles. This model controls for income and age, using 401k eligibility as our instrument. Take a look at the highlighted coefficients in this data output. At the 25th percentile, the effect is approximately 1,252 units. This more than triples to 4,500 at the median and reaches nearly 9,800 at the 75th percentile. Notice the dramatic trend. The effect at the top of the distribution is nearly 8 times larger than at the bottom. This clearly demonstrates the heterogeneity that a standard OLS regression would completely mask. All these estimates are highly statistically significant, with p-values well below the 0.01 level, confirming that 401k participation has a powerful and unequal impact across the distribution of wealth. Now let's look at how to interpret the results from our IVQR model. In this practice step, we focus on reading the output table. For the 25th quantile, representing households with low savings potential, 401k eligibility only increases assets by about $1,250. At the median, the effect is moderate at $4,500. However, for high savers at the 75th quantile, the program is extremely effective, boosting assets by nearly $10,000. Our inference check shows that all p-values are below 0.05, and confidence intervals do not include 0, confirming statistical significance. In conclusion, these results reveal that the policy exacerbates wealth inequality by benefiting the rich far more than the poor, a nuanced finding that standard OLS regressions would simply overlook. To wrap up the analysis, let's visualize the results using the estat coefplot command. This plot compares our IVQR estimates, shown by the orange line, against the OLS average, represented by the green dashed line. The upward slope of the orange line clearly shows that the treatment effect increases as we move up the wealth distribution. Notice the bias. The average OLS estimate overestimates the impact on the poor at the lower quantiles, while significantly underestimating the benefit for the wealthy at the top quantiles. This visualization provides a clear, intuitive argument for why quantile-based analysis is superior to simple mean-based models in this context. After running our IVQR model, it is crucial to perform diagnostics to ensure our results are valid. First, we test for constant effects using the command estat endogeffects. The null hypothesis here is that the effect of 401k participation is constant across all quantiles. Looking at our output, the chi-square value is 45.20 with a p-value of 0.0000. This means we reject the null hypothesis, confirming that the effects are heterogeneous and that using the IVQR approach is necessary rather than a simple IV model. Next, we address the issue of weak instrument robustness. Standard walled intervals can be unreliable if instruments are weak. By using estat dualci, which inverts the rank test, we obtain a robust dual confidence interval. In our case, the interval is between 3,500 and 5,800. Because this interval excludes 0, we can confidently say the effect is significant even if our instruments were weak. The IQR estimator relies on a grid search algorithm, which can sometimes run into issues if the true coefficient is outside the default search range. Looking at the charts, Chart A demonstrates good convergence with a clear global minimum in a convex walled statistic. In contrast, Chart B shows bad convergence, where the curve is monotonic, indicating the minimum lies beyond our current search bounds. To fix this, you can manually widen the search range using the bound option, for example, setting it between negative and positive 20,000, and increasing the number of grid points with ngrid. If adjusting the grid doesn't work, an excellent alternative is to switch to the smooth estimator, which uses a different optimization method that doesn't rely on this type of grid search. To wrap up, let's review our key takeaways. First, heterogeneity matters. Relying only on mean effects like OLS can obscure distributional realities, as policies can have vastly different impacts on the poor versus the rich. Second, handling endogeneity requires IVQR. Standard quantile regression fails when selection bias is present, but IVQR effectively combines the granular detail of quantile regression with the causal identification power of instrumental variables. Finally, for Stata users, the new IVQregress suite in version 18 is now the standard. You should use IQR for rigorous inference with single endogenous variables and smooth for speed and more complex models. For deeper study, refer to the seminal works by Chernyshakov and Hansen and Kaplan and Son listed here. Thank you for your time.